Section 6.3, Logarithmic Functions. In this section, you're going to convert between exponential and logarithmic equations. You're going to evaluate logarithms. You're going to use the common logarithms. You will use the natural logarithms. In 2010, a major earthquake struck Haiti. 1 year later, another stronger earthquake devastated Honshu, Japan. Even though both caused substantial damage, the earthquake in 2011 was 100 times stronger than the earthquake in Haiti. How do we know? The magnitude of earthquakes are measured on a scale known as the Richter scale. The Haitian earthquake registered a 7.0 on the Richter scale, whereas the Japanese earthquake registered 9.0 on the Richter scale. The Richter scale is a base 10 logarithmic scale. In other words, an earthquake of magnitude 8 is not twice as great as an earthquake of magnitude 4. We compute it this way. So we compute it based on base 10. We say it is 10 to the 8 minus 4, which is 10 to the 4th power. That is 10,000 times as great. In order to analyze the magnitude of earthquakes or compare the magnitudes of two different earthquakes, we need to be able to convert between logarithmic and exponential form. For example, suppose that the amount of energy released from one earthquake were 500 times greater than the amount of energy released from another. We want to calculate the difference in the magnitude. The equation that represents this problem is, we say 10 to the x power is equal to 500, where x represents a difference in the magnitude on the Richter scale. How should we solve this x? So if you notice, in the past we had 2 to the x power equals to 4, and we were able to predict what x is because we know that 2 raised to the second power is 4, which means in this case x is equal to 4. However, in this specific case, we have not yet learned the method for solving exponential equations. None of the algebraic tools discussed so far is sufficient to solve this equation. We know that 10 to the second power is 100. We know that 10 to the third power is 1,000. But notice how 500 is in between 100 and 1,000. So 10 raised to what power should be 500? So that is the question. As you can see here, when we graph that 10 to the x power, notice how this value right here represents when the magnitude or the difference in magnitude is 500. And that number isn't a clear number. We know when it's equal to 1, when it's equal to 2, when it's equal to 3 and 4, but that x happens just between the 2 and 3 somewhere. To find an algebraic solution, we must introduce a new function. Observe that the graph passes the horizontal line test, which means the exponential function y equals b to the x power is 1-to-1 function. So its inverse is going to be x equals b to the y power is also a function. As in the case with all inverse functions, we simply interchange x and y and solve for y to find the inverse. To represent y as a function of x, we use a logarithmic function of the form y equals log base b of x. The base b logarithm of a number is the exponent by which we must raise b to get that number. We read the logarithmic expression as the logarithm with base b of x is equal to y, or simply log base b of x is y. We can also say b raised to the power of y is x. So that is how we convert from logarithmic into an exponential form. Because logs are exponents, after all. For example, the base 2 logarithm of 32 is 5, because 5 is the exponent we must raise to 2 or apply to 2 in order to get 32. So 2 to the 5th power is equal to 32. We can also write log base 2 of 32 is equal to 5, and we we read it log base 2 of 32 is 5. Here is the general rule that we're going to follow in order to convert from logarithmic form into an exponential form and vice versa. If you have log b of x equals y, we're going to take, first of all, b here is the base of the logarithm, y is the outcome of the logarithm, and the x is the argument of the logarithm. So in this case, we say base raised to the outcome will give you the argument. So base raised to the outcome will give you the argument, and that is how you're going to convert from logarithmic form to an exponential form. And you can do the opposite as well. So if you have this expression and you need to convert it to a logarithmic form, you're going to say this is logarithm of the base b, and that would be the answer, and that would be the argument. So the argument, and that is equals to the exponent. So that is how you're going to convert back and forth. Let's try some of these problems. Convert to a logarithm the following questions. The first one, 5 to the second power is 25. We know that this is logarithm base 5 of the answer equals 2, which means if you raise 5 to the second power, you will end up with 25. So that is what this means. Second one, we have 5 raised to the negative 2 equals 1 over 25. This is log base 5 of 1 over 25 is equal to negative 2, which means if you raise 5 to the negative 2 power, you will get 1 over 25. And then we have 25 to the half equals 5, which is log base 25 of 5 equals 1/2. That means if you take the power 1/2 to 25, you get 5. The next one, log base 5 of 1 is equal to 0. In general, log 1 is equal to 0 no matter what the base is, because we know that in order to make any number into 1, you have to raise it to the 0 power. Next one, we have log base 5 of 5 equals 1. That is, if you raise any number to the power 1, it gives you the same number. So that is another fact that you can remember. When the base is equal to the argument, the answer is always 1. When this number is equivalent to that number, the answer is always 1. I will do some of the second questions on the side because they don't have a space. And then I'm going to erase my answer, and hopefully you're taking notes while I'm doing it. The first one, we have y equals log base 2 of 8. We need to find this without using the calculator. So we're going to convert it into an exponential form. We say the base raised to the y power is equal to 8, and we know that 8 is equal to 2 to the third power. Now we have the same bases. We can compare the exponents together. So from the comparison, we find that y is equal to 3. So that is for A. B, we have y equals log base 2 of 2. This converts into 2 raised to the y power is equal to 2. The bases are already the same, so we can compare the exponents together. And the exponent, if it's not there, it's equal to 1. So that leads to y equals 1. I'm going to erase what I did. Number C, we have y equals log base 2 of 1. And that converts into 2 raised to the y power is equal to 1. There is only one solution, is when y is equal to 0, we will have the answer equal to 1. So that is the answer for, let me write the answer here, y equals 1, y equals 0, y equals 1. And for the first one, we got y equals 3. So these are the answers. Let me highlight them. I'm going to erase, and I will do D. Y equals log base 2 of 1/8. We convert it into an exponential form. We get 2 to the y power is equal to 1 over 8. I know that 1 over 8 can be written as 8 to the negative 1 power. And 8 is basically 2 to the third power. So I can rewrite this as 2 to the third power raised to the negative 1. Now I'm going to multiply the exponents together. So I will have 2 to the y power equals to 2 to the negative 3 power. By comparison, because the bases are the same, I can conclude that y equals negative 3. So y equals negative 3e. I have y equals log base 8 of 2. So convert it. I will get 8 base y equals 2. I know that 8 can be written as 2 to the third power. So 2 to the third power raised to the y power equals 2. I will erase and finish the work down. So now I can multiply the exponents together. I will have 2 to the 3y equals to 2. By comparison, I notice that 3y is equal to 1. I want to solve for y, so I'm going to divide both sides by 3. I will get y equals to 1/3. And that is accurate, because if you take the cube root of 8, you will get 2. So y equals to 1/3 in this case. Again, I'm going to erase my area here, and then I'm going to do the last one here. Y equals log 2 of 0. Y equals log 2 of 0. This means, if you convert it, raise 2 to any power to get 0, and that is impossible. So there is no solution in this case. It's undefined. There isn't a number that you can raise 2 or apply it to 2 in order to get 0. So we understand that log 0 is undefined. If you plug that into your calculator, it's going to give you an error. So we're going to say here does not exist. Last one, it doesn't exist. Okay, because this will never happen. There is no y to satisfy this equation. Okay, so now that we discussed the meaning of logs, and we know now that the logarithms are basically another form of exponents, we have two types of logarithms. The first logarithm is what known as the common logarithm. A common logarithm is a logarithm with a base 10. We write it log base 10 of x, or simply omit the 10 and just write log of x. So if you see your logarithm without a base, the base is automatically going to be 10. The common logarithm of a positive number x satisfies the following definition for x is greater than 0. We know that y equals log base 10, the 10 usually is not written, of x, is equivalent to 10 to the y power equals x. So when we convert it to an exponential form, if the base isn't there, we assume it's 10. We read log of x as logarithm with base 10 of x, or log base 10 of x. The logarithm y is the exponent to which 10 must be raised to get x. So that is the meaning of it. Another type of logarithms is what we call the natural logarithm. A natural logarithm is a logarithm with base e, which is the Euler number, 2.718282. We write log base e of x, or simply ln of x. So when you see ln, that is another log. However, this log is a natural logarithm which has a base e. So in other words, log base e is equivalent to ln. The natural logarithm is of a positive number x satisfies the following definition for x is greater than 0. y equals ln of x is equivalent to e to the y equals x. We read ln of x as the logarithm with base e of x, or the natural logarithm of x. For short, I say ln, but it is the natural logarithm. The logarithm y is the exponent to which e must be raised to get x. That is basically the meaning of the logarithm or the natural logarithm. Since the function y equals e to the x and y equals ln of x, or the natural logarithm of x, are inverses, the function natural logarithm of e to the x is equal to x. In other words, ln cancels the function e because those are inverses of one another, and that happens for all x. So, few facts that we collected from here. We say log base, any base of 1 is equal to 0. We learned that. We also learned that log base b of b is equal to 1. We learned that log base b of 0 does not exist. We learned that log of x is the same as log base 10 of x. We learned that log base e of x is the same as the natural logarithm of x. And we learned that the natural logarithm of e to the x is equal to x. And I also can claim that e to the natural logarithm of x is equal to x because these will cancel one another because those are inverses of one another. So far, these are the facts that we collected that are not going to change no matter what happens. These are facts that you have to memorize about the logarithms. And then we also learned the conversion fact right here, which allows us to convert from logarithmic form to an exponential form and vice versa. If you have any questions, let me know.